Well, you have to go in and you have to select. What I do is I just got where I leave my computer on my desk, and then I'll remote into it from the house and upload the videos once they. So guys, we need these. Y'all want to work? Okay, so here we're looking for. We're going to design a Zener regulated power supply. And so we're going to take our unregulated DC. And so this is basically all we need to draw. Then we're going to have an RS. Then we're going to have our Zener. We're going to put it in there reverse bias. Now this is a positive supply, right? Yeah. And then our load is going to connect right there. You don't even have to draw the load. That's the output of the supply. Well, it depends. Here our load is going to vary between 0 and 10 milliamps. So that means this power supply is going to be designed so we can unload it. But it's only going to be a 10 milliamp supply. So what's the first thing I need to... yeah, well, the input, the swing of the input. So my input, my unregulated DC is going 10 volts plus or minus 10%. And this is DC, so my V in max would be equal to, what's that? Okay, would be what? 11, yeah. And my V in minimum would be 9, right? Okay, so these are my two. So my input, my unregulated DC. So coming in here, we have what? We have unregulated DC. And then out over here, we have regulated DC. Which I think we can call DC out. That's fine. So I've got my minimum and maximum voltage. So I know my AC is going to vary between that range. Now I need to figure out this guy right here. We'll call it RS, and we'll call this Z1. So what I need to do now is what? I need to figure out the voltage that's going to have to be dropped by the Zener. What's our Zener voltage, by the way? Okay, so 5.1 volts. So we know that RS is going to have to drop the difference between the Zener voltage and the, or the output voltage and the unregulated input. So first thing I'm going to do is I'm going to take VRS max would be equal to 11 volts minus 5.1. So what's that going to give me? Yeah, 5.9. I don't run out of room. And my VRS minimum is going to be my minimum input voltage, which is mine, minus 5.1. So what's that going to give us? 3.9. So now I know the voltage drops that I'm going to use to calculate this resistor. So what we're working on is R is equal to V over I, right? Everybody okay? So RS, what V are we going to use? Which one of these V's are we going to use? We're going to use the minimum because we're going to set it at pretty close to the knee. So if the voltage drop across the Zener goes, the resistor goes up, it's going to move. The current's going to go up, and it's going to move it toward IZ test, right? Or the test current. So we're going to use it 3.9. Okay, so what current are we going to use? Max. Plus IZK. Yeah, because what we're trying to do is trying to make sure that we're going to do this. So what we need to do is we need to figure out what IZK is. So where did y'all find it? What? Yeah, so what you did is we're all doing the 40, we're all doing what? The 4700 series. You got your worksheet? Yeah. So we'll look up IZK. So what our maximum current is 10 milli. And then we're going to add to that our IZK we're going to get from our data sheet. What did you get, Drew? 1 milli? Okay, so we're going to use here's the answer sheet. Yeah, one first one. Okay, gang, so what would RS be equal to? What's the calculated RS? We're not going to use the calculated RS, but what it's going to do is going to give us what to choose, right? So what's our calculated RS? What's that? No, that's what we're going to use. What we want to do, we want our calculated RS. That's 354. Okay, so the key must be wrong. What'd you get through? 364? You did get 54? So 39, it's 39 divided by 11 milli. Yeah, 354. Now you got to make sure you add IZK to it. Did you add IZK? In fact, I got 354. Okay, so what we're going to do next? So you had to use the internet for this thing, right? I'll print that off. So what we'll do is we'll look at the standard resistor chart and figure out which one we're going to do. And what are we always going to do with this guy? Always. Which way we're going to always round down. So here's our standard resistor values, 5%. So I find one that's down below. This is 10%. I don't need to put that. You can't even buy 10% resistors anymore. Standard and the cheapest ones now are your 5% resistors. Used to, we had 20%, and then we had 10%. These were carbon resistors. And then now we went to what they call the thin film or the carbon film, and they make these 5%ers all the time. So I'm going to come up here, I'm going to look and see 354. We're not going to use 360. The first one we're going to look at is what? Yeah, 330. Are we okay? So RS, this is going to be temperature. I'm going to use 330. I'm going to multiply that by 1.05. And why is that? Yeah, so what we're doing is we're checking to make sure we cannot use a resistor bigger than that. That's the absolute maximum that would put it at IZK. So what we're going to do, of course, this guy here is obvious it's going to be okay. And what do you come up when you multiply it by 1.05? Anybody got it? 346.5. This guy right here is fine. As long as it's what? Less than that. If it came up to be equal than that, then you'd probably go down one more, right? So RS is going to be equal to 330. What wattage rating do we need on this? We'll calculate that later. So remember, resistors, you have two things. And when I say two things, some people say the tolerance, but every device has a tolerance on it, right? You understand that? So we're looking for the unique things that make up a resistor. So when I buy a resistor, of course, you're going to have to specify three things. You're going to have to specify what? You're going to have to specify the ohms. You're going to have to specify the watt, the watts, and of course the tolerance. But when I say the two things, these are the two things I'm interested in. Of course, I might put that on test. Probably on every test that we've got. In fact, I think these are on there Because if you got to go out and buy these parts, you got to know how to buy them, right? You just can't go in and say I need an NPN transistor. Huh? What's that? You'd be surprised. For some reason, people want to say both. I don't know, but I guarantee you, I don't know about this class, but we got a few people absent. We got 2 people absent. It wouldn't surprise me if I put volts on there. Somebody would put volts. Okay, so let's go ahead and calculate the wattage. So PRS, and of course the formula I'm going to use is V squared over R. Now you can calculate current, but we're going to use the maximum voltage. That's when it's going to produce most power. So I'm going to use 5.9 squared over, not the calculated value, the value you end up using, right? Y'all understand? 330. That's one of our power formulas. V squared was R. And by George, you should have those formulas in your head. Ohm's law. So when I come up and I say what's I equal to, you shouldn't even think about it. You shouldn't have to write down the little color wheel. You should have those 2 laws. Your Watt's law and your Ohm's law should be in your head. Now the derivatives of Watt law are pretty complicated, especially when you get into the V squares and the I squares. But those 3 main formulas, what's the 3 main power formulas? P is equal to what? V times I, or E times I squared R, and V squared over R. Well, you're going to have to round it eventually, because if you come up with a 0.3224, watt resistor, there's no such thing. So what you do is you go up to the next higher value. So why round it? I mean, if you're going to use a calculator, why round it, right? So what I would do is I'd say 5.9 squared. If you say 6, if you round up, I would definitely not round down. If you want to round this number, I would round up. Because if you round down, you could end up with a wattage rating that's lower than what you need. If you round up, you'll never get a wattage rating lower than you need, right? So I understand your question now. Yeah, you can round up, but don't round down, right? So yeah, we could use 1/8 of a watt right here. So, but when you use the key, don't round down, because yeah. So I've got 105.5 milliwatts is what I got, and of course they don't make 105.5, so we go up to the next standard value, right? So quarter watt or 1.25 is close to that, so I'd go up to a quarter watt here. But on the test, I'm not going to ask you which one you'll choose. I'm going to have you calculate the actual this, because some of y'all don't know the standard values of wattage ratings. What's the standard value, by the way, anybody know? Wattage ratings. On the radial lead, on actual lead resistor. So 1/8, quarter, half, 1, 2, 5, and then after that they write the wattage rating on the side. So above that you can get all different types of wattage ratings on these resistors. So a quarter watt would be 125 milliwatts, but this is 105, so that we want to make sure we go up to the next higher value, right? Besides for the one we calculated. Okay, so what else we need now? Yeah, well, what we need to do is we need to calculate and make sure we don't exceed the wattage rating of the Zener. Okay, so we're going to choose the right resistor. So now what we're going to do is we're going to make sure we don't exceed the wattage rating of the resistor. I'm sorry, the Zener. So power the Zener, which formula we're going to use? We're going to use V times I, the main formula that all other formulas came from. So, of course, our voltage is pretty easy. This is going to be VZ. So what's VZ? Yeah, so we use 5.1 because that's the voltage that's being dropped by the Zener. And what current are we going to use? Well, we're going to use the maximum current that the Zener will ever handle. So to calculate that, what we're going to do is we're going to come over here and take our maximum voltage across that resistor. That's the maximum voltage across that resistor, and that resistor is in series. So all the current in the circuit is flowing through that Zener. It's flowing through that resistor. So I'm going to divide that by the size of that resistor, not your calculated size, your used size. And so this is going to give me maximum current flow. Multiply that times the Zener voltage, and this will give me my Zener power. 5.9 divided by 330 times 5.1 equals 91 milliwatts, 91.2 milliwatts. And then I turn around and write it wrong. Is that right? So we could actually use another Zener, but we're using 1 watt Zeners here, so we have no problem. So is there anything else we need? I don't think so. 92 milliwatts, and that's all there is, and you've just designed a Zener regulated power supply. Well, what things do you need to know? First of all, you need to know your unregulated end, how far your unregulated end is going to change. And you need to know the current is going to be required by the load. And after that, you choose the Zener, you choose the resistor, you choose the wattage rating on the resistor, and you've got a Zener power supply. And these guys are used all over. Very simple. And you'll see this done sometimes where you have a chip that's a regulator chip that regulates unregulated DC, but it needs to be powered up. It's 723, which is a real nice variable regulator chip, really nice. Well, you power it up with a Zener. So you have a little Zener power supply to power the chip on your unregulated side, and then it drives transistors to run your power supply. 723, LM723, great little chip. It can sense overcurrent. You put a little series drop-in resistor, very low value out there on your output. You know, it'll shut down for overcurrent, over voltage. It's a nice little chip. So we okay there? Any questions? And all the rest of them are basically the same. I mean, depending on putting your. What do you mean? Yes, we do, but we did it right here. So that's my formula right there. So I think the sheet said you take that value and put it in there. What I did, I don't guess I should have done that. I saved the step. You'll see what I did, yes or no. So right here we calculated maximum current. That's IRS max. We multiplied it right there. I just didn't write the value down. So what was the value? So I don't think I can write anymore. Huh? Oh yeah, I can escape right here. No, it won't let me do that. But I don't want to keep, I want to discard them. I should have, so another one y'all want to work? Which one? Number 3, design and draw a Zener regulated power supply using the following parameters. We got unregulated voltage, we got a negative voltage, so this is a negative regulator. So what my zener will look like is my got ants. And so here's unregulated N. Here's my RS. Here's my zener. Because this is negative, we have to put the zener in there reverse biased, right? And this is going to be my load. V out. That's supposed to be a V, though it looks like a U. My V out is going to be minus 22 volts. And my load current is going to change. I load is going to vary between 10 milliamps all the way up to 15 milliamps. My input regulated voltage, my unregulated voltage is going to be what? 26 volts. Plus or minus, what's our percentage? 10%. So you have to be careful. If you put that diode in there forward bias, it's going to act like a diode, right? You understand? It's going to conduct a lot of current, probably burn your little resistor up over there. A little RF is probably going to go out to lunch. Okay, so let's calculate Vn max, and let's calculate Vn minimum. So Vn max is going to be 26 volts. By the way, minus or plus, you know, when you put these in the formulas, you want to do the absolute value of these. If you don't, you're going to come up and get a minus R, and you don't have minus R. Plus 2.6 volts. And then my Vn minimum would be 26 volts. 26 minus 2.6 volts. So what we got for Vn max? $28.6. What do we get for Vn minimum? Are we okay? Everybody okay? Lost anybody? Everybody okay? You okay, Drew? Look kinda, I don't have my glasses on. Okay. Huh? And of course these are minus. So we're okay. Huh? That's 10%. 10% of 26 is 2.6. Are you okay? What's that? Yeah, it's a negative supply. So my input is swinging from negative 20 minus 26 plus or minus 10%. But when you calculate these, right, you understand that you need to use the absolute value, or you're going to have to treat it with signed numbers. So I got a minus, minus. So when you got a minus and a minus, what do? When you subtract, change the sign, substitute, and add, which is going to put you in the wrong direction. You're going to come up to be more negative, right? So this is not minus a minus, this is minus a plus. And a lot of people get confused with that. So VRS. So what we're going to do is we're going to drop the sign to keep y'all from getting confused. But you got to understand this is a negative supply. The Zener's in there back upside down. It's not in there back. It's in there reverse bias. We can't say it's in there backwards because this is the way these guys are supposed to run, right? So the maximum voltage that resistor is going to drop, and it's going to drop a voltage, is going to be, what's our Zener voltage? 22 volts. So the maximum voltage it's going to drop is going to be 28.6 minus 22. What do we got? Is that a minus voltage or a plus voltage? It's a voltage. It's a voltage. It's not a minus voltage. It's a voltage. We don't want, and this is what I'm talking about. When you're calculating voltage drops, they are voltage drops. It's just that if I put my meter, and if I put my black lead there and my red lead there, it's going to measure a minus voltage, a negative voltage. But if I swap them around, it's going to measure a positive. So it's a voltage drop. And VRS minimum is going to be 23.4 minus 22. So how much is that voltage going to drop it there? 4 point what? Oh yeah. Should have done that in my head. So now we need to calculate the size of RS. So RS is the minimum voltage, which is what? 1.4 divided by the maximum current. What's our maximum current? 15 milli plus 1 milliamp. That's a 22 volt Zener. I thought they dropped down to lower when they got up that high. Huh? So you got to look up these guys. So what's it say? It says 0.25. See that through? Oh, it's 25. It's 250 micrograms, right? I thought I remembered that. The higher the voltage, the less IZK goes. IZK. What is a 4728 though? You got to use a 22 volt Zener. Yeah, but you got to use a 22. You got to use a 22 volt Zener. You just can't choose a number. You got to use one that's got a VZ of 22 volts. So you just can't say I'm going to use a 1N4760. Understand what I'm saying, Tarek? So what you got to do is you got to do what? You got to go over there on that VZ. You got to find one that says 22 volts, and then that's the one you're supposed to use. Are we okay? So what's our calculated value for RS? We're okay? Okay. So 67 ohms. Of course, we're going to go down to the 5%. We're going to try what? We're going to try 62. Y'all understand that? So I'm going to say 62 times 1.05. What does that give us? 60 what? Yeah. So it came up to be less than that, so it's going to be okay, right? So what we're doing, y'all understand why we're doing the tolerance? Because if it's greater, so you got we say 5%, but y'all know it's not 5%. What is it actually? It's plus or minus 5%. So it could be 5% too high, or it could be 5% too low. If it's 5% too low, that's not going to hurt us because we're putting more Zener current and we're moving away from the new. If it's 5% too high, that means we could go out of regulation, right? You understand that? So we check that, double check it, everything's okay. So RS is going to be 62 ohms. Now we're going to calculate the power. PRS would be equal to the maximum voltage it's going to drop, which is 6.6 volts squared, divided by the size that we chose, 67 ohms. So what we got? Huh? Oh, okay, I'm sorry. We chose a what? 62. See, so I made a common mistake that students made. And that's not a dot, that's 62. I just didn't erase it. No, Joe. That was right. The top one was right. The bottom was wrong. So y'all watch out for me. They're going to take care of me. 6.6 squared divided by 62. So what did y'all get? Yeah, we just round this guy up. I mean, so this is milliwatts. So what are we going to have to use there? At least a what? So what we're going to have to use there? There's no such thing as a 702 milliwatt. I gave y'all the, huh? There's no such thing as a 3/4. I gave y'all the values. What's the values? So we got an 8. Okay. Then we got a 1/4. Then we got a 1/2. You put a 1/2 watt in there, it's going to burn it up. Because this is 125 milliwatts. This is 225 milliwatts. This is 500 milliwatts. Right? And then 1, so we have to use at least 1 watt. 1/2 watt would burn up. In fact, probably what you do, what we usually do is we go up and then we actually go up 1 more, so we probably use 2 watts. Okay, now we need to make sure we're not going to burn up our Zener. So PZ would be equal to my Zener voltage, which is 22. We got a real high voltage right there, so that means it's going to produce a lot more heat for the current that we're doing. And what's the maximum current flow through our resistor? Let's do it that way this time. Not when we calculate power is power. It's going to drop 22 volts. Y'all understand that? So if you use negative 22, you're going to come up with a negative wattage answer. You understand? So when we calculate our resistor size, we're going to use absolute values. Right? You understand that? Now I'm going to have to make sure I put my Zener in there right. I got to make sure I know that this is going to be a minus 22. But if you come in here and try to use that sign math in there, you're going to come up with negative resistors. You're going to say, I'm going to put a negative 62 ohms in there. I mean, you would be in business. You got yourself a superconductor, right? You understand? You got a piece of something that's actually got negative ohms, which there is no such thing as negative ohms. Now, we can get real close to zero, almost zero, with what we call superconductors. But that's something, and not unless you're in the military, you know. I think the Navy's got some of their ships that uses superconductors. I think the rail guns that they shoot, it's got so much power, uses so much power, uses superconductors. But you're not going to see superconductors when you're there. So are you going to ever, if you ever come up with an answer that is negative ohms, what do you know? You know it is wrong, right? So what we do is we shift so if I come up and I get negative watts, is there such thing as negative watts? So yeah, Brandon, if we use negative 22 volts to calculate our power, because it's dropping 22 volts, right? You understand? It don't make any difference if it's negative or positive, it's dropping 22 volts. So let's use, so when I calculate my current through my resistor, am I going to use negative voltages? No, I'm going to use what? Absolute values, right? So IRS max, the maximum that resistor is going to ever drop is what? What's the maximum voltage that resistor is going to have to drop? Here's my two voltages. Okay, so I'd say, so max would be 6.6 volts divided by the size of the resistor. Is what? 62. And so when I calculate PZ, I'm going to use 22 volts plus or minus. Yeah, absolute value, right? Y'all know what the absolute value is. What's the absolute value? What is the absolute value of a number? It's the number without the sign. So it's basically plus, you're right. Times whatever answer we got up there. Of course, what did we get up there? 6.6 divided by 62. Okay. Then we're going to subtract from that the current that's going to the minimum current. So this power supply is never going to run unloaded. So that means even on our maximum voltage, there's going to be load current out there. So what's our load current? What's our minimum load current? 10 milliamps. And this is milli too, by the way. So a while ago we used 0, so that power supply could be unloaded. Here means if we got a load that's pulling current all the time, then that will never be Zener current, and it will allow us to use a smaller Zener. Now, if the load ever opens up, it's going to burn your Zener up, but you know you got bigger problems. You got big problems anyway. So what did we come up and get PC? So what Zener did we choose? A 1N 47 48. So when you do your Zener lab, that's what you're going to have to do. You're going to have to ask me for a Zener. And you'll have to ask me for a resistor. And when you ask me for a resistor, you got to tell me two things. What's the two things you need to tell me? Yeah, the ohms and the watts. That's your. What? 2.3 watts. So what did we do? So what did we do, guys? So somebody tell me what's wrong. Okay, so tell me what's wrong. Nobody knows. Nobody knows. I guess I've been in here in the field quite a long time, and I know when we got a problem and when we don't have a problem. But I know what Zeners I'm using. I know I'm using the 1N. I'm trying to use the 1N4748. Well, on the very first page of the 1N4748, one of the first things they give you in a data sheet on the Zener is the wattage rating on the Zener. If you exceed the wattage rating, what's going to happen? You're going to mess up. So I'm going to come up here and I'm going to look at this 1N47. It's a 1 watt Zener. Our design is going to require how much? 2. So what does that mean? We're going to burn that sucker up. So what does that mean? That means we cannot use a 1N4748. We would have to find probably a 4 watt Zener. Wouldn't use a 2 either, right? You understand that? Probably won't be able to buy a 3. I've never heard of a 3 watt Zener, but I'm sure there's a 5 watt Zener. So you'd have to go up. You understand that? So we went through all the works, we did this, we did that, then we come up and we found out. And that's what we're doing. So that's what you're doing. That's why you verify the wattage rating on your Zener. But you'll have people that do that. I know I told you about the power supply story, right? Where they were supposed to load their power supply with a 100 ohm resistor. And they was grabbing these little 1/4 watt resistors that came in the lab kit. That's back when they used to have to buy their lab kits. Now we furnish them. And they were burning them suckers up because they didn't do what? They didn't calculate the power of the resistor. They just said, okay, the lab said put in a 100 ohm resistor. What did they do? They put in a 100 ohm resistor. Something's wrong with my power supply. It keeps burning up resistors. You got your worksheet? Huh? Here's the key. So that was an interesting one. That was one a little more challenging, right? For one thing, we didn't work with negative voltages last time. When we went over these things in class, we didn't work with negative voltages. How many of you got your Zener in there right? You did? How many knew we was going to burn up the Zener? Yeah, and that's one of the first things you need to find out right off the bat. So now Zeners are rated in a lot of different things, but what's the two primary things Zeners are rated in? Watts and volts. That's their two primary ratings. Then they have a tolerance, right? You'll understand that. And then they got IZK and IZT and all that other kind of stuff, right? You understand. But it still has It has a voltage, it has a wattage, and it has a tolerance. So you need to know all three of those when you buy it. So you could find out, we could probably find, what'd I say, 5-watt Zener. But the internet is so neat. I mean, good gracious, you can just come in here and just type in that 12 volt 5-watt. So we need a 22 volt 5-watt. See if we can find one. Yeah, so Mauser's got one for 12 cents. Mauser's a good company too. So there we go. It'd be interesting to look up the number, so that would be, so we're set to go. So, but if we don't understand that, it's just like putting the wrong resistor in there, right? You don't understand that. Just looking at the value and not considering the tolerance and not considering the wattage rating. Huh? Inconsiderate, right? You'll end up burning up a bunch of stuff and blame it on one thing when it's actually you that did it, right? Okay, guys. Any problems with Zeners? I don't know when's our next test. I think it's after midterm. Yeah, I think. I'm not sure. I got it. This book's laid out different than the other books that we're looking at. We're not going to look at renewable energy. Power supply troubleshooting is a good one. Linear power supplies are fairly easy to troubleshoot. So what do they talk about next? What's chapter 8? So I'll put this worksheets up there, the answer sheets up there, and I've tried to make a habit of doing all the calculations on how I came up with stuff too. Which hopefully, if you find any problems with these calculations, I have to key in all these formulas. They don't pop up there instantly. I don't know if y'all played around with the formula thing on Microsoft Office or Microsoft Word. Now I know y'all can get Microsoft Word for free, right? When's the last time you went on the college's homepage? It used to be in the pictures. It's Office 365, 365, and it's the whole version. It's free. All you got to have is a Lawson State email address. I don't know if it's still in the crawl or not. The pictures they sent across there. It was last time I looked. Yeah, there it is. And so you go right here through Office 365, free. Can't beat it. So it was slide number 10. I think it's got a link to the slide too. I think you just click on that and it should, I think, I might be wrong. Yeah, so here it is right here. So all you have to do is just click on the slide and it'll take you to the page that shows you how to do it. Okay guys, y'all go ahead and take a 10-minute break.